In this video, let us learn about the motion of a charged particle in a uniform magnetic field. Let us consider 4 different cases. First case is charges at rest in uniform magnetic field. Second case, when velocity and magnetic field are parallel or antiparallel. Third case, when velocity and magnetic field are perpendicular. And the fourth case, velocity and magnetic field are at any other angle. Let us consider the first case, that is when the charge is at rest in magnetic field. That is for a stationary charge. For a stationary charge, velocity will be equal to 0. And we have the expression for magnetic force. Magnetic force F is equal to Q into V cross B. Or magnitude only we can write F is equal to Q V B sin theta. Here, since velocity is equal to 0, putting the value there in the equation for magnetic force, you will get force is equal to 0. Therefore, no magnetic force will be acting on a charge at a rest which is kept in a uniform magnetic field. As a result, it will continue its state of rest. Second case is when the charge moves parallel to the magnetic field. Here we can see the charge is moving in the same direction as that of magnetic field. That is, velocity and magnetic field both are in the same direction. Therefore, the angle theta between velocity and the magnetic field equal to 0 degree. So, sin theta equal to sin 0 equal to 0. Therefore, the magnitude of magnetic force F is equal to QVB into 0 equal to 0. That is, when a charged particle moves parallel to the field, the magnetic force acting on it will be 0. Since no force is acting on it, it will continue the same motion according to Newton's first law. It will not deviate from its path, its speed will not be changed. Okay, it will continue the same motion because the magnetic force is 0 in this case. Next, suppose the charge is moving anti-parallel to the field, that is in the opposite direction of the magnetic field. Here you can see the charge is moving towards left, magnetic field is toward right. That is, the angle between velocity and the magnetic field is 180 degree. Both are anti-parallel. We know sin 180 degree is equal to 0. Therefore, the magnitude of magnetic force F will be equal to QVB sin theta equal to QVB into 0. Again, you will get 0. Therefore, if the charge is moving anti-parallel to the field, there will be no magnetic force acting on the charged particle. So, it will continue the same motion without changing its speed, without deviating from its path. So, in the second case, if the charged particle is moving parallel or anti-parallel to magnetic field, the charge will continue the same motion because the magnetic force on the charged particle is 0. And next, let us consider the third case where charge is moving perpendicular to the field. Here, the magnetic field is towards right and the charged particle is moving upward direction. That is, the angle between velocity and the magnetic field, it is 90 degree. When theta is equal to 90 degree, sin theta is equal to sin 90 equal to 1. Therefore, magnitude of the magnetic force will be equal to QVB sin theta, that is QVB equal to VB. Therefore, here the magnetic force is not 0, but the magnetic force is QVB. Let us consider this case in detail. When the velocity of a charged particle is perpendicular to uniform magnetic field, the particle moves in a circular path in a plane perpendicular to B, that is magnetic field. The magnetic force Fb acting on the charge is always directed towards the center of the circle. That is, if the charged particle is moving perpendicular to the magnetic field, it will experience a magnetic force equal to QVB. Also, it will follow a circular path. Why it is following the circular path? Let us see here. Suppose the charged particle is at the point A and the magnetic field is into the plane. That is why it is represented using crosses. The charged particle is a positively charged particle Q, and at the point A, its direction of motion is along right. That is, the direction of velocity is towards right, and we know at this point it will experience a magnetic force equal to QVB. Now let us find out the direction of this magnetic force. To find out the direction of the magnetic force, we have to use right hand rule. So let us use it. Use the thumb of your right hand, stretch it in the direction of velocity, that is towards right. Stretch all other fingers towards magnetic field, that is in the direction of magnetic field, means into the plane. See in which direction your palm points. It is in the upward direction now. Therefore, the magnetic force will act towards upside, in the upward direction. It is shown in the figure. As a result, the charged particle will deviate its path a little towards upside. Now suppose the particle is at the point B. At this point, the direction of velocity is given in the upward direction, and here the charged particle will experience a magnetic force QVB, and let us find the direction of the magnetic force. Again, you use your right hand rule, that is stretching thumb in the direction of velocity and other fingers in the direction of magnetic field. You can see your palm points towards left. That is, magnetic force is towards left. It is shown in the figure. As a result, the charged particle will deviate its path towards left, and suppose it reaches the point C. Again, the charged particle will experience a magnetic force equal to QVB at this point C, and let us find the direction of magnetic force using right hand rule. Stretch your thumb in the same direction as that of velocity and other fingers into the plane, that is in the direction of magnetic field, and see the direction of magnetic force. It will be same as that given in the figure. And at each and every point in this manner, we can find out the direction of the magnetic force. At all points, the magnetic force will be having same magnitude QVB, but you can see at each point the direction of magnetic force is changing. We can see always the magnetic force is directed towards a center. That is, magnetic force will act as a centripetal force. Centripetal force means a force acting towards a center. Since magnetic force is always directed towards a center, this magnetic force will act as centripetal force. You know, a centripetal force will provide a circular motion. Therefore, in this case, the magnetic force will provide a circular motion of the charged particle. That is why when the charged particle moves perpendicular to the magnetic field, it will follow a circular path.